All right. Hello, everybody. My name is Megan Tillman. I am a graduate student at Rutgers University, working with Blakesley Burkhart and all these collaborators listed up here on the low redshift Lyman alpha forest and supermassive black hole feedback. So first, just go over a little outline here. See if I can get that. Perfect. So first, I'm going to talk to you about why I love Simba, and you should too. It is a very interesting simulation. It does a lot of things very differently. Is it the most accurate simulation? No, they're all wrong. But it's interesting and it's a good test case. I'm going to talk why we need to model AGN feedback. I'm going to talk about specifically Simba's AGN feedback, what makes it so effective. I'm going to talk about the Camels project, which I'm sure you've heard a lot about, hopefully, over the past few weeks. How we can explore feedback models with it, looking at AGN and both stellar feedback. And then I'm going to talk about the interplay between stellar and AGN feedback because they have a very interesting interaction with each other. So why do I love Simba? It's not just because it's a very cute baby lion. So if we recall from a very distant few minutes ago in Blakesley's talk, we have the photon underproduction crisis where we need additional heating in simulations to actually match the low redshift Lyman alpha forest observed data. And we have the fact that AGN feedback models will affect the forest based on how they're implemented. So let me raise you one. Simba's column density distribution function. That looks incredible compared to all these other column density distribution functions we're seeing from these hydrodynamic cosmological simulations. So the AGN jet feedback plays a particularly significant role in this match. This was discovered by previous studies on other Lyman alpha statistics already. We just happen to look at the column density distribution function. So if you remove the jet feedback, you get this red line here, and you can see how different that is. So why do we need to model AGN feedback? Can't we just lump this into the UVB? That's much easier to put into simulations. It's much less expensive. Can we lump it in? No. Look at that difference. You may say that's just a normalization difference. I'll prove to you later that it's not because we did fitting with UVB rescaling. But first, let me try to logic my way through why we need to include feedback in simulations. Specifically AGN jet feedback, because that's not often included in simulations. So first of all, observations tell us that there are jets. We see them, we should put them in simulations. I know it's expensive and frustrating to model because we don't have good motivation for building these models, but that's why we need to build lots and test. We also need to make sure that we don't tunnel vision on a single statistic. Even if this was correctable by just rescaling the UVB, we have no idea what other statistics we're messing up because we removed this jet feedback. Maybe this affects something else. We have to remember to explore other avenues. So now let me talk about a more quantitative reason why we need to include AGN jet feedback. So Simba's jet model affects the column density distribution function in ways that the UVB cannot. And let me prove this mathematically. So what we did is for Simba with jets and Simba without jets, we rescaled the UVB in each case to find the best fit. So without jets, we need a UVB that is 2.7 times stronger than the Hart-Maddow UVB, which could be reasonable. There have been studies that have found a UVB that could be that much stronger. And that gives us this chi-squared value right here. None of these reduced chi-squared values are close to 1, but it's astronomy. We work on orders of magnitude, and we're not statisticians. The important thing here is we're looking at quantitatively which of these is a better fit. So the best fit without jets is worse than both the best fit with jets and the fiducial fit without rescaling anything. So here is the best fit for the Simba model, including AGN feedback. That reduced chi-squared value is much smaller than the other one. And just the fiducial Simba results, the reduced chi-squared value is smaller than the UVB rescaled best fit for no jets. So, and if you look closely, the best fits are the green lines. So the dashed green line is no jets, and then the solid green line is with jets. Look at that slope change. AGN jets affect the slope of the column density distribution function. This is not something that the UVB can do. This is probably something that other things can do, and we should look for those other things. But clearly from here, we can see AGN jets are one of those things that need to be explored in this context. But we also need more observations. So this is my one of probably a couple desperate pleas to try to get more low redshift, Lyman alpha forest observation telescopes out there. We need more space-based telescopes in the far ultraviolet, please. All right. So let's talk about Simba's AGN feedback. Why is the jet feedback so effective? Why is it doing this? So the UVB is a very isotropic thing. It affects everywhere all at once the same way. Jets are kind of the opposite. So they're highly collimated. They're more localized. They're not isotropic. So they are going to affect things differently at different column densities. They're not just going to have a normalization effect. There's an included decoupling time in these jets. This one is very important. Stellar feedback models have done this for years, and I don't know why we're not doing this on all of our AGN feedback models. Decoupling is very important in cosmological simulations because they have very low resolution galaxies, so your winds, your feedback is going to be damped. You need to do a decoupling time, and this needs to be motivated by zoom-in high-resolution simulations. So this allows the jets to escape the galaxies without being damped and actually affect like the CGM and the Lyman alpha force, the IGM, and gives us the results that we see. These jets are also heated to the virial temperature, so they actually heat the gas where they end up. When they recouple, they can actually heat their surroundings. That is what actually causes the heating of the IGM. So just to visualize this, we have a little GIF here of with jet feedback on the top and without jet feedback at the bottom. You can see on the right the temperature projections. On the top, you can see just how much those jets are actually heating the IGM. It's crazy the difference with and without jet feedback. This is still including their other feedback mode. Simba has 2 feedback modes, well, it's 3, but just think about jet and radiative. And on the left, you can see the neutral hydrogen column density projection. And you can see it's kind of blasting voids into the neutral hydrogen. It's really removing a lot of that neutral hydrogen from the column densities that are associated with the Lyman alpha forest. We also know it's not just heating the gas, it's also ejecting gas. So this plot is from Christensen et al. 2020. On the left, you have just fiducial Simba results, temperature density projection. On the right, you have the no jet results. So if you look at the red points are the gas that's ejected by the jets. And they track it between the simulations. So on the no jet mode, they're not actually ejected by the jets because there's no jets, but you can see where that gas would be if it was, if the jets were on. So you can see by looking at the black points, you are pushing a lot of gas into the WIM from the diffuse. So you are just heating a lot of gas, but you're also ejecting a lot of gas. And this is being seen from the percentage of the gas in the halo, the percentage in the condensed region, the percentage in the diffuse. You are moving a lot of gas around. And as Lacey talked about, that's kind of what we need to change the slope of the column density distribution function. All right, so let me talk about Camels. Camels is very, very exciting. Stands for cosmology and astrophysics with machine learning simulations. I know a lot of people here love machine learning. I don't do it right now. I might do it in the future. Please do machine learning for me. So there's over 4,000 simulations in the Camels project that explore different parameter variations of right now what's publicly available is the Simba and TNG subgrid models. So these are 25 megaparsecs co-moving boxes with periodic boundary conditions. There's 256 cubed particles. That's a mass resolution of about 1.2 times 10 to the 7 solar masses. It's low, but there's a ton of simulations. And it's sufficient for the Lyman alpha forest. And this allows us to actually explore the variations in Simba's feedback model because Simba is one of those subgrid models that's explored in Camels. So let me show you some cool movies that Paco made because these are very exciting and I'm sick of talking. So here we have 3 different simulations. Astrid is not yet publicly available, but I think it will be soon-ish. Don't quote me on that. We got illustrious TNG, and we have Simba. And you can see Simba's heating up a lot. Those are those jets that popped on. TNG, you have much less heating. It's very isotropic. That's just how the AGN feedback works in TNG. It chooses a random direction to eject kinetic energy in one of their modes, but it averages out to be isotropic over long periods of time. Astrid's supermassive black hole feedback model is very similar to TNG. It's just weaker. That's like the main difference between them. So you can see how much of a difference this makes in temperature by redshift of 0. So they all start the same, and then it heats up. If we get a closer look at Simba specifically, kind of rotating around to help visualize when the actual heating from the jets becomes volume filling. So we got that first one that kicked on around 5, C of 5. Not volume filling at all, very, very localized, all the way up until, even at redshift 1.5, it's not. And then as Blakely mentioned, once you get around redshift of 1, it becomes more apparent that this heating is volume filling. And this is what's necessary for us to observe these statistics, at least in the column density distribution function. So, talking specifically about what parameters we can vary in the Simba suite with Camels. So 2 AGN feedback parameters varied. First one is momentum flux. Here are some equations. I don't expect you to read them, but I can talk about them if you want. And we also vary the jet speed. More equations. So maximum jet speed gets up to about 8,000 kilometers per second. These jets can reach distances of about 10 kiloparsecs before they recouple back to the gas in the simulation. And by the time they recouple, they lose about maybe 1,000 kilometers per second due to just gravity. And so maximum jet speeds at edge of the galaxy can be around 7,000 kilometers per second. And that's what's necessary, apparently, to actually propagate these effects out to the IGM. This number can vary. We also look at stellar feedback parameters that are varied in Camels. We look at the mass loading factor, equations for mass load. And we look at the wind speed. Again, I can come back to these. They're also in the Camels paper. So let's look at these AGN feedback parameter effects on the column density distribution. So on the left here, we have variations due to the jet speed. On the right, we have the momentum flux. Red lines, more red means the higher the parameter value is. Depending on the parameter, it can get either 2 times or 4 times stronger than it is initially. This is a lot. That's because the point of this is to really determine what's going on. It's not to produce a bunch of realistic simulations. It is to produce a bunch of simulations that you can apply machine learning techniques on. And to do that, you really need to know the effects of these feedback models. The more blue the line is, the lower the parameter value. So you can think of it as red is stronger feedback, blue is weaker feedback. So largest effects are seen at the lowest column densities. The highest column densities, 15 to 17. Around 17 is where you get to alignment limit systems, can be galaxies. 15 to 17 around here can be also CGM inside halos. It's very noisy because Camels is a small box. I plan to produce a lot more sightlines to get this less noisy, but for now, you don't really need to worry about this because the observational data here is pretty high. The error on the observational data is pretty high. So hopefully we can reduce that in the future. But for now, this is what we have. And we also see that jet speed is the dominating factor. This makes sense. Jet speed was the one that affected the Lyman alpha forest when we looked at all of the different feedback modes in Simba. Looking at the stellar feedback, okay, this is crazy. This shouldn't be happening, right? Stellar feedback can't reach the IGM. It looks just like the AGN feedback effects. So the suspicion that you might have come up with, because everybody here is very smart, much smarter than me, strong stellar feedback could suppress supermassive black hole growth, and that could suppress AGN feedback, and then we'll see the same effects. And this is what we checked. So checking this, looking at the interplay between stellar and AGN feedback, and I'll try to go through this fairly quickly because I'm running out of time. So what statistic did we look at? Number of supermassive black holes in the simulation. Less supermassive black holes means less AGN feedback. We also looked at the fraction of supermassive black holes in the jet mode. This is the mode that actually affects the forest. And we looked at average Eddington ratios because the jet speed scales with this. The smaller the Eddington ratio, the larger the jet speed, up to some cap. Right. Eddington ratio is the, is that 3? Okay, perfect. Eddington ratio is the ratio of the instantaneous supermassive black hole accretion rate over a maximum theoretical accretion rate based on geometry. It's not actually the maximum. We see super Eddington accretion in observational data. It's kind of like, so just think of it as an accretion rate that we can compare supermassive black holes of all masses. That's a very useful statistic for people who look at black holes. So here are all those statistics. On this plot, we have the number of black holes in the volume, and we have the fraction of those black holes that are in the jet mode versus redshift. The solid lines are the number of black holes. The dashed lines are the fraction of black holes in jet mode. And on the right, we have the average Eddington ratio. This dashed line is where that maximum velocity cap is hit. So everything above this is going to have less than 7,000 kilometer per second jet speed, and everything below will have 7,000. So first thing you see, as we increase the stellar feedback mass loading parameter, there are less supermassive black holes in the simulation. This is important, okay? So less supermassive black holes, less feedback. That makes sense. But more of those black holes are actually accreting in the jet mode. So they're producing more jet feedback, even though there are less supermassive black holes. But we have slower jet speeds. So all of this adds up to some complicated scenario, which ends up being a generally positive feedback where the stellar mass loading factor means more jet mode feedback, which means less neutral hydrogen. So the mass loading actually increases the jet feedback's ability to remove neutral hydrogen from laminar pores. For the wind speed, it's much more intuitive. There's less supermassive black holes as we increase the stellar wind speed. And there are fewer actually jet mode accreting supermassive black holes. And this means that the higher the wind speed of the supernovae, the less AGN feedback is actually going to be able to affect the forest, which means that supermassive black hole growth is very, very suppressed. And so this kind of just all illustrates that we really need to consider AGN feedback and stellar feedback together because their interplay is very complex. And so we can't just pick one or the other. We also need to be constraining the UVB at the same time. There's so many things to think about, and we can't think about it all, and it's frustrating. But it is exciting because jet feedback is clearly very interesting, at least in the Simba simulations, and we really should explore more models of jet feedback. So another little movie. If you look, the black dots and the red dots are the supermassive black holes. And as you go to the right, when you increase the wind speed, you can really see that the number of black holes in the simulation is decreased. And that is what causes this very dramatic reduction in heating from the AGN jets. So conclusions and outlook. AGN jet feedback can have a significant and unique from the UVB effect on the low redshift Lyman alpha forest. It affects the slope, the UVB cannot. So exploration of current and new AGN jet models is vital for further constraints of AGN jet feedback. And for this, we need more observational data on the low redshift Lyman alpha forest. We need new telescopes. In order for jets to be effective, specific conditions must be met. That's that decoupling, that's that collimation. And finally, the Camels project provides a unique opportunity to explore stellar and AGN feedback with machine learning techniques. Just because I didn't do this doesn't mean that you shouldn't, because Camels is amazing, and I recommend you all go work with the data. Thank you.
So we have questions. Hey, thank you very much. This is Martin Ray. Yeah, thanks a lot for sharing. This is triggering a lot of thoughts in my brain. So sorry if my question is not super well posed, but if we start twiddling so much with the AGN feedback, we're really messing up with the absorbers around really massive halos. Is there not information that we can get from the spatial distribution of these absorbers, basically a correlation function of the laminar flow forest? Both of you, both Blakesley and you have shown mostly the cumulative distribution function, but what's preventing us from extracting biases or correlation functions to try to really pinpoint the scales at which these processes stop acting?
Time.
Okay.
I feel like if more people were working on this, we'd be able to figure out a lot more stuff, but it's just us. So.
But there is no data limitation. We actually have this correlation function at Redshift 0.1.
I feel like I'm not the best person to okay.
Okay. Right. Yeah, it sounds like someone should.
I think this is, yeah, something that a lot of people are starting to look at more, is just this jet feedback and what it's actually doing to like cluster group statistics. And I know Ramil's looking at that a lot. And yeah.
Hi, Richie Wong from Stanford. A really nice talk. Two related questions, one following Martin's. So have you checked other observables that's affected by changing your wind speed? Like, does it change the SFR of galaxies? You know, does it change the just basic scaling relations that are consistent in the fiducial model? But if you're trying to match the CDD, you know, by changing the wind speed, like what other observables does it change? And secondly, can you also do the same thing for something like TNG? Like if stellar feedback and AGN feedback are now coupled like this way, can you just, you know, tune any physical model to match the observables you're tuning to here?
I'll answer the second question first because it's easier. TNG, they're just tweaking the different AGN feedback parameters for TNG doesn't actually affect the forest. We haven't found a parameter yet that tweaking will actually be observable in the Lyman alpha forest. So unfortunately, we can't really do that with TNG yet. And could you just repeat the first?
Yeah, just other observables that might change,
right?
Changing the wind speed.
I've only looked at the Lyman alpha forest. I'm a third year, so this has been all of my work in grad school. I'm sure there are lots of people in Camels who are looking at these other parameters and how they change with.
Hi, I'm Tan from here UCSB. Actually, I'm from the same group as his. So I have two questions. One question is like, if you guys consider the degeneracy between the whatever feedback model and the UV background on the CCD and on other observation parameters you have. And the second question is just curious. Have you guys tested the B parameter with all the feedback model, like if it's affected, the B parameter, if it's affected by all the feedback?
As far as we can tell in the simulations, the B value is definitely affected by the jet feedback, and I think also, well, it is affected by all these AGN feedback parameters. I have a love-hate relationship with the B value. It's a good statistic to use. I don't like it in simulations. It's hard to fit, and I'm avoiding it at the moment. But it is definitely affected by it, so it would be a good one to go revisit eventually. And as far as like fitting, so one of our next steps, I think, is if we go back to these, we want to rescale the UVB to then see, you know, how much of the slope is changing. We also want to fit to see which of these would be a best fit to the observational data if we allowed the UVB to vary, because we know that Hart-Medal probably isn't the right UVB. I mean, probably none of them are the right UVB at low redshift. This raises a lot of problems for the UVB at low redshift, because if we tune to Lyman alpha forest statistics at low redshift to find the UVB, then we're probably including AGN jet feedback effects in that inherently. It's complicated. If AGN jet feedback really does affect the forest, like something like this, then that makes using these statistics to actually find the UVB challenging at low redshift. But we do plan to do best fits to figure out which of these parameter variations.
Thanks.
Hi, Chris Lovell. Amazing talk. I had one comment on just the kind of galaxy properties. So kind of related to Peter's comment, if you could combine this with, you know, say SSFRs and things like this, in Simba at redshift greater than 2, it really underpredicts the fraction of passive galaxies. So it seems like combining this analysis with that would be able to give us some really good constraints on these parameters. So should do that. I think that'd be great. My comment though, my question though was about environment. So if you compared the small Camels boxes to the larger Simba box, and do you see any effect there? And is there a way of, sorry, maybe I missed.
No, it's my extra slides.
Ah, great. And I guess related to that is, do you see an environmental effect around, you know, more massive halos that you don't get in Camels, for example?
Okay, so something interesting about, so this is something I still need to check, but I have a suspicion of what's causing it. So black solid line is the Camel Simba, and dashed black line is the original Simba. So it matches very, very well for most of it. I mean, this is all noisy because we don't have enough sight lines yet. Up here is a mismatch. Camels is lower. It looks like it's heating more than original Simba. And I think that's because the box is smaller and these jets might be passing over because of the periodic boundary conditions and just overheating slightly more than Simba. I need to check this. I think I can just compare the temperatures between the two simulations, and that should give me an idea of whether it's that or not. Right, so that's the difference between original Simba and Camel Simba. Did that answer your question? What was? Yeah, because there's not as many massive halos in. But from the movie, there's clearly like plenty of jet mode supermassive black holes to heat the IGM. So.
Right, we have time for one quick question. Somewhere, yeah.
Thank you very much for the talk. I'm Dalia Baron. I wanted to ask a more general or simpler question about the AGN feedback in general in Simba. Why is it so differently implemented than in Illustris? What is the difference in the radiative and the kinetic mode? Whether it's just, you know, that they have the jet mode very strong and the radiative mode very weak, and why they decided to do it like this, and whether they still reproduce the observed properties of local massive galaxies, although the feedback is very different from Illustris.
So I know that some of the galaxy properties are about on par with how well TNG or Illustris matches, and then some of them aren't, like entropy profiles aren't matched well in Simba, whereas in TNG they're better. As far as why the jet mode is in Simba like this, I mean, we see bipolar jets observationally. I have to assume that was part of the motivation. I can't go inside Ramil's brain because he's like beautiful minded this model because it works so well, but it seems very unintuitive. The decoupling was definitely a motivation from like stellar feedback models need decoupling to make sure they don't get damped. These winds are the same. They'd probably blow apart the galaxies if it wasn't decoupled. Highly collimated so they could get out of the galaxy. TNG includes a kinetic mode that is like a random direction, like kind of like a jet, but it has a wider angle and it doesn't decouple. So I don't know why TNG doesn't include jets, probably because it's very complicated and not well motivated. Well, we see jets, but it's hard to create a model that like is right because we really don't know much about supermassive black hole feedback. Yeah, I mean, I don't know. I can't get inside Ramil's brain, but Simba's model is very interesting, and I think it provides it's a really good benchmark for we really should look at more jet feedback models because they give really interesting results. Simba is an interesting simulation. I really like it.
All right. So let's thank the speaker.